Okay, hi again everyone. Here we are back with our Calculus 3 class notes, and I'm working up towards example 26. We're on page 27. I'm calling this video example 26D because we worked up towards it. So finally here we are, example 26. Consider the position function or the vector valued function r of t, which is 2 cosine t in the I direction plus 3 sine of t in the j direction plus 4 t in the k direction. And we want to consider that specifically at time t equals pi over 2. So we want to find the velocity, speed, and acceleration vectors of a particle whose motion in space is given by the position vector r of t. So the velocity vector is the derivative of the position vector r prime of t. So the derivative of 2 cosine t is minus 2 sine t. That is in the I direction. Again, we're able to take the derivative in each direction separately. So 3 sine t, the derivative of that is 3 cosine t. That's the j direction. And the derivative of 4t is 4 in the k direction. So that's the velocity at any time t. The speed is the magnitude of the velocity vector, which just means we square each component, add them up, and take the square root. So minus 2 sine of t squared plus 3 cosine of t squared plus 4 squared is 4 sine squared t plus 9 cosine squared t plus 16. We can pull out a 4 from the first two terms and get 4 times sine squared t plus cosine squared t leaves us with a 5 cosine squared t plus 16. So sine squared t plus cosine squared t obviously is 1. So that's 4. 4 plus 16 is 20. So we have 20 plus 5 cosine squared t all under the square root. So that is the speed at any time t. The acceleration of our particle at any time t is the derivative of velocity, which is the second derivative of position. So we just take the derivative of velocity, and we look back up here. The derivative of minus 2 sine t is minus 2 cosine of t in the I direction. The derivative of 3 cosine t is minus 3 sine of t. That's in the j direction. And the derivative of 4, a constant, is 0. So this is the acceleration vector at any time t. So in part B, let's find the particle's speed and direction of motion at t equals pi over 2. That just means plug in t equals pi over 2. So we already have speed at any time figured out. So all we have to do is plug in pi over 2 into our formula now for speed. So we plug in pi over 2 here. So cosine of pi over 2 is 0. So cosine squared of pi over 2 is also 0. So we have just the square root of 20. 20 is 4 times 5, so that's 2 times the square root of 5 when I take the square root of 4. The direction of motion simply means the velocity vector made into a unit vector. Okay, so we take v of pi over 2, and then we divide it by its magnitude. So we just found the magnitude to be 2 square root of 5, which is the speed. And the velocity vector itself at pi over 2 is just minus 2 times the sine of pi over 2. Sine of pi over 2 is 1, so that's minus 2. Cosine of pi over 2 is 0, so that's 0, and then 4. So minus 2 divided by 2 square root of 5 is minus 1 over the square root of 5i. 0 divided by 2 square root of 5 is 0. And 4 divided by 2 square root of 5 is 2 divided by square root of 5 in the k direction. Find the parametric equations of the tangent line to r of t at t equals pi over 2. Okay, so what we have to remember what we need for the tangent line. We need a vector that is parallel. So a vector that is parallel would be r prime, evaluated at pi over 2, because r prime is tangent to our curve. And then we just need the terminal point of the vector r of pi over 2, because r of pi over 2 points to the point that's on the curve. So the terminal point of that would be 0, 3, 2 pi. So there's our x naught, y naught, z naught. So we have our x naught, y naught, z naught. We have our vector that's parallel, and it's easy to put in there into our parametric equations form. So we have x equals x naught plus v1t. X naught is 0. v1 is minus 2, so it's just minus 2t. Y equals y naught plus v2t. Y naught is 3. v2 is 0, so y is just 3. And z equals z naught plus v3t. Z naught is 2 pi. v3 is 4, so 4t. I'll go ahead and finish this up really quick. The last page in this section of section 13.1 of notes are differentiation rules for vector valued functions. So if u and v are differentiable vector functions of t, c is a constant vector, capital C with bolded in here is a constant vector. Little c italicized here, that represents a scalar or a real number. So c is any scalar and f is any differentiable scalar function. not a vector function, just any differentiable scalar function. So you have the constant function rule, the scalar multiple rules, the sum rule, the difference rule, the dot product and the cross product rule are both just product rules. You can kind of see how they work easily. And then the chain rule, which is similar. So these rules are all very, very similar to what you're used to. Just take a look at them and make sure you understand how they work.